Hello, chemistry students. I hope you're staying safe from the coronavirus. I am here with my parents in East Greenville, Pennsylvania. You can hopefully see behind me my parents' massive orchard and farm they have going on. So, kind of crazy, but it's nice, beautiful, and a chilly 48 degrees right now. But I'm recording outside because there's lots of activity inside. So hopefully you can join me for Chapter 17, Nuclear Chemistry. If you picked up your packet early, you probably don't have the notes in that. That's okay. You can download them in the comments section. Or in the sidebar of this video, I'll put a link to my Dropbox that you can get them. Just be aware of that, but hopefully you should be able to get the notes and fill them in as we go along. Let's start with 17.1. That is on radioactivity. Let's begin. Now this is different than just about anything that we've talked about before. Nuclear changes involve changes in the nucleus of the atom, whereas chemical reactions deal with electrons. We were so focused on the first 16 chapters about what happens outside of the nucleus that we didn't even talk about what happens on the inside. We know the nucleus contains the protons and neutrons. Protons are positive, neutrons are neutral, but we never really talked about what could happen in the nucleus. And it turns out that these isotopes that we've talked about all year as having different numbers of neutrons. The same number of protons and electrons, they do the same thing. They can be different nuclearly, I think that's a word, even if they're the same chemically. So they may behave the same chemically, make the same bonds, etc., etc. But nuclear reactions may change how these specific isotopes function. And we divide these isotopes into stable and unstable. Stability is when you have a predictable, chemically bonding, normal atom. However, some atoms are just naturally unstable. They may spontaneously break apart. It has nothing to do with what's around them. It has nothing to do with how they've bonded to something. It's just simply to do with their nucleus and whether or not it is intact or not. And you can see that there's a band of stability. So let's say here's the protons here. Where's my mouse here? Here's the number of protons. Let's go with a very well-known atom. Oh, there it is. Let's go with sodium. It's number 11. Sodium's right about here. So you can see, if you go to about here, sodium is stable within a very short range of neutrons. It's stable with 11, 12, maybe 13. If you get up to 20, you can deal with a very unstable sodium. Or maybe you're dealing with an atom that's 56, like iron. Well, iron is stable up to about 85 neutrons, but if it had 56, it would be very unstable. So you can see there's a band of stability. Anything outside of that is unstable. It may spontaneously break apart. A nuclide is a particular type of nucleus with a specific atomic number or number of protons and a specific nucleon number, also known as mass number. It's the number of protons and neutrons in the nucleus of the atom. So consider the fact that this is how we write the nuclide symbolism. Nucleon number up here. Atomic number down here, the element here. So if we're dealing with carbon, carbon has 6 protons, and if it has 14 as its nucleon number, that means it has 8 neutrons. You see, you subtract 14 minus 6. This is the total protons and neutrons, and then this is just the protons. So protons and neutrons minus protons makes the number of neutrons, which would be 8. The 13 over 6 carbon has 7 neutrons and 6 protons, making a grand total nucleon number of 13. Radioactivity is a phenomenon of energy released from certain elements and isotopes. Carbon 14, or 14 over 6, and carbon 13, 13 over 6, they will bond the same. They will both, if bonded with 4 hydrogens, make methane, CH4. Chemically, they act the same, look the same, etc. But nuclear energy and nuclear chemistry, when you study that, you can see that carbon-14 acts wildly different. Well, why? Because that extra nucleus makes it just a little bit too large to be stable. Think about it in terms of weight. Okay. Now, this is my disclosure here. I'm 6 foot tall and 180 pounds. Okay. That's normal. If I was 200 pounds, would I be stable? Yeah, I would be. If I was 220, probably still stable, just a little bit heavier. But there comes a certain point where my body starts being negatively affected by my size, my mass. If I was 600 pounds, I'd be the star of a reality TV series, My 600-Pound Life. Same thing with nuclides. Carbon 12, normal. Carbon 13, normal. A little bit heavier, that's fine. Carbon 14, a little bit unstable. Carbon 14 will disintegrate after a couple thousand years, crushed under its own weight. Carbon 15, it would just be crushed instantly. It just can't exist. It's too large. Flip side, how about carbon 11? That's a little small. Carbon 10, couldn't exist, too thin. Kind of like an anorexic carbon. So I like to think of neutrons in terms of weight. Now, obviously, there's a massive difference between human body index and chemical and nuclear chemistry, but get the crossover. And that's all for this lesson. So make sure you do your section reviews, 17.1, page 289. I think there's only a couple questions, so it shouldn't be too hard. And tune in tomorrow for 17.2 on nuclear stability.